Hi, welcome to the second part of this tutorial series about nodal setups. I'm going to do a quick point of situation, and then I'm going to move forward to look into vector data. So previously, I focused on scalars, booleans, and integers as a way to address concepts that deal with programming, that deal with building up my own logic in the node editor, that deal with being in control of values, being able to limit them, to interpolate them, decimate them, etc. So moving forward, I'm going to look more and more to vector data. So vectors here are just basically an array of three scalars. Instead of having one numbered line and picking one value, I have three numbered lines and I pick three values. And so it's like having a list of three scalars. Of course, these might mean different things depending on what they're used for. So for example, for color, this might just be color RGB sliders that allow me to pick a color from the possible colors. For positions, well, they are the coordinate axis from which these values define a position in a 3D space. For directions, they come from positions, but they don't care where the position is at. They just care where the position is looking at. And so this is something that is going to be also very used. Vector data can be also used to pack information. So in this case, with Euler angles, with the direction node, I'm just basically a list of three rotation angles that I'm going to apply to an object or to some vector to orient it. So not exactly something we can grab, but just some values that are to be applied to. And we have here some transformations. So I'm going to look into scaling, rotation, and translation. So the basic motion transformations. I call translation, in Lightwave we call it position. I call it translation here, or could also call it move. It's just that I like to make a distinction between position, which is a property of occupying a location in 3D space, and translation or move, which is the transformation of that property. But in the end, sometimes I interchange between the two with some freedom, so don't mind that. And then we're going to look into matrices. So I'm going to have here the 3x3 matrix, and plus translation, we have the 4x4 transformation. So we're going to look into more things like dot product, cross product, axis, angle, rotation, etc. But this is a good summary. So most of the time, it's going to deal with positions and also with directions. So in this case, I have here this cube mesh, and you can see there's some positions with these magenta vectors. They're pointing at the point positions of the mesh. And in brown, we have these normal vectors, which are representing the direction, a direction that is perpendicular at the vertices. So we can access these through, for example, through the spot info node when we are in the displacement node editor. And you'll notice that I have object spot and world spots, for example, for the position of the vectors. The difference, so this is something that I'm going to insist at times to kind of understand what's the, because it's very important. So we have all the time these data inputs and outputs as well. And sometimes we really have to grasp what's the context of that data. Where does that data come from? Because, well, object spot and world spot are referent to the same thing, but they're in different states. So object spot are the positions you have when you open the model in Modeler. The world spot is dependent on the evaluation point of the scene. So for example, if you're rendering, everything already happened. You already have had your simulations, your animation going, your displacement, etc. So it's after everything was solved. But when we are, for example, in the displacement node editor, maybe that's not decided yet. So for example, we have this drop-down menu that allows us to choose what's the evaluation point that the displacement node editor is going to take place. So it can be after morphing, before bones, before local displacement, before wall displacement, and that's going to change the information that comes out of world spot, because it's going to be dependent on where is it taking the information of the vertices from. So for example, if I put before world displacement, this means that the world spot is going to output the point positions after the object has been moved, rotated, scaled, etc. And it's going to be quite different from the object spot at that point. So these are the sorts of data we're going to transform and worry about. Here I have basically the same thing, but it's done by Denis Pontonnier nodes nearest point and point info. Here I get the index, and here I get the object position, the world position, the object normal, and the world normal. So again, in many places, object actually kind of means like whatever you see in Modeler. The data is in the same state as it is in Modeler, and world is the evaluation point, the current evaluation point. So it's going to depend on which node editor you are, and what evaluation point is being used by that node editor. Okay, so I'm also going to look into some concepts that kind of pop up everywhere. So for example, there's one which is decomposition and composition. So for example, many times, especially since we're dealing with vector data that is packed, we're gonna decompose it into things and then compose it back into what it is. So this is going to happen with not just positions, but also many times you need to convert things into another type of interpretation of positions, etc., and then put it back together. So decomposition and composition are very common practices to basically be in control of specific parts of data, or just extract a portion, etc. So another very common practice is to do conjugation, that I've spoken before about it. So we have a main operation to be performed, but before and after I do two operations that allow me to change the context in which my main operation takes place. And so this is also very common because many times you have to do a game of give and take. And so that's something that I shall call your attention for as well. So let's look a little bit here in Lightwave node editor and this sphere in the displacement node editor. I have some nodes here. So I have a constant vector node, a constant color, and a constant direction node. And they all have different UIs, as you can see, but even though they output all scalar values. So it's just a bunch, it's just an array of 3 scalar values. Of course, here in color, we can also see the 8-bit color format, but the data that actually goes by is the one on the right. So this means that I can, even though these things are supposed to be used for different things, I can use the same vector nodes to manipulate all of them. So one of the most basic things to do with some vector data is to get one channel of it. And so we have the native vector scalar node that allows me to get several types of information from one vector. So I can get the X channel, the Y, the Z, can get the value of the channel that has the maximum value, the minimum value. I can get the length of the vector, in this case for a position that is useful. It's basically the distance from that position to the origin. Or I can also have here in the color, I have the same type of information. Instead of X, Y, and Z, I have red, green, blue, but the scalar value is the same. The only difference is that instead of length, I have luma, which is a sort of a grayscale. And these are made explicit by Akira Sasaki vector to XYZ and color to RGB. So here you have, instead of having a list, we have them exposed, all of them. So you can see the only difference is the length and the luma. To be honest, the one I probably use the most is the split vector by TrueArt. So it's very easy to just come here and have quick access to all 3 channels, instead of having to copy, for example, this 2 times to plug in and then choose the appropriate channel. So no, not much of a fuss here with this one. So I really like it, and you'll probably see me using it a lot. So these are ways to split the vector into scalars. So in here I have ways of putting scalars into vectors. So the native make vector, it's quite useful for that. Then we also have one by by Akira Sasaki that basically allows me to replace just particular channels. So here I have this vector -1, 2, and 0.5. And if I put it here and I put this 0 value, let's say here in X, now it's 0 to 0.5 instead of -1. So I replaced only the X channel. So this allows me to save some time and not having to split everything and combine everything back together like I would have to do here. If I would wanted to do that this way, I would have to make 3 connections. Here I just have to make 2, and that's nice. So this split and make vector routine is going to be very common, especially when you want to be in strict control of how things happen per channel. And so it's something that's going to be used over and over again. Falls back into this routine of decomposing and composing. The same for these here. So here I'm decomposing into scalar amounts. Here I'm decomposing into vector amounts. So for example, here I have this vector -1, 2, and 0.5. and I multiply it by a vector 1, 1, 0. This means that I'm going to bring the value on the z-axis to 0. So what happens is this value becomes 0, and instead of 0.5. Now I could, for example, multiply these values also by 0, 0, 1, basically the complementary of this one. And now this will just pass the z value. So here I have 0, 0.5. So this is a way to filter out channels that I don't want. And in a way, this allows me to process these values not as scalars, but as vectors. And so this might be a requirement for something I'm doing. Even though, of course, if I connect them back together, I get back the same value in this case, but I was allowed to edit these components separately, or these vectors filtered in this way separately. Now here I have another decomposition in composition. I have this vector 1, 2, 3, and here I can get its length, so the distance that goes from the origin to the position that is being defined here, 1, 2, 3. And so this is going to give me the length. And so with the normalize, I can get access to a vector that is just like this one, but it has length 1. So it's basically like a copy of this vector, but with length 1. So if I put here this length vector, you can see that it comes out 1. So that's the length of that vector. They combine together with a scale node. They give me back what I had. So if I come here, you can see that I have back 1, 2, 3. So this is another way to decompose and compose back a vector, or to infer information from a vector. So let's move back down here. And so here I have some examples of nodes that have a good equivalent node for vector data. So here I have the sign, here I have the absolute, the invert. This one is for color, but it works the same. I have the floor, clamp, multiply. In the case of the multiply, I have here basically the same thing, and I have also a scale. So the scale will multiply the vector by a scalar. And so it's going to be, I can of course do the same. Let's say that I come here and I have a scalar, constant scalar, and I'd say I'm going to multiply by 2. And so if I plug this either in the scale or in here, it's going to give me the same output. So you could say, why do you need this node? Well, this node is probably more correct for some operations, even though the result is the same. But it kind of is obvious about what it's doing. So if I have this around here, it seems that I'm multiplying two vectors together. And here it's very explicit. I'm multiplying a vector by a scalar. So whenever, like I've said in other times, whenever I can be explicit about what I'm doing, the better it is for me when I read back my node tree some weeks later. So some of these nodes are from third parties. The sign node and the clamp node are from Akira Asagi. The absolute, the floor, and the invert node are from TrueArt. So I'm very thankful for them. Now, there are cases where you don't have and you might end up having to start to be creative. Here's an example. So here is the compare vector node, which is very useful to check for a case that sometimes is very dreadful, which is when you have a zero length vector, meaning a vector that is at the origin, 0, 0, 0. So sometimes you really don't want this, especially if you're going to deal with multiplications. This will bring everything to 0, 0, 0. So you really want to check at times for this or for direction. So a vector that is 0, 0, 0 has no direction, no length, and sometimes you want to avoid that. So we have here the compare vector node, and it's checking for that with a certain tolerance. And of course, if it is 0, 0, like it is here with the swap vector, I'm going to replace it by 1, 1, 1. And so this is a good way to check for that. Now imagine that I want to do this check per channel. Imagine that I want to do a multiplication and I want to weed out zeros but per channel. So if I put here 2, this is 2, 2, 0, 0, and so the compare vector is not going to catch it, and I'm going to get just same thing. And so the y and z channel are going to be 0. Maybe I don't want that. So how could I go about it? Well, one creative way is to basically divide the value by itself, and so whatever is 0 is going to come out 0, and whatever is not 0 is going to come out as 1. So with that, I can invert it. meaning subtract that to 1, 1, 1. And so whatever was 0 becomes 1. And so now the z-axis that was 0 here is 1. So I add that to whatever I had in the beginning. And so now I basically filtered that 0 out from this vector. Instead of having 0 on the z-axis, I have 1. The only issue with this is that I have no tolerance, meaning if I want to catch some floating point error or check from a value that is getting really close to 0, I don't have a way to do that. So if I want to do this, I have to go the long way, the long boring way, which is to split the vector and do the compare and swap per channel. So that's why I have here 3 of these, so I can do that per channel. It's not very optimal, but sometimes you have to pay that price. And so there's something that happens with other vectors as well. If I want to use the round node, I don't have a vector version like I have here for the floor. So I have to split the vector, do the round per channel, and make vector. Same for power node, same for copy sign, etc. So there are all these sorts of nodes that you might have to do the split and make vector. It's a bit annoying, but it's the only way to go about it at times. Now I'm going to just demonstrate something that I've demonstrated for scalars, which is to solve the issue of copying a sign, but maybe with a little twist. So here I have this power node, and if you remember, if I put negative values in here with some values that are not integers, so for example here I have -2, and if I have 1 in here, I'm gonna have -2. It's all good. But if I put, let's say, 1.5 in here, I'm going to get this error. This error tells me it's not a number. And we've seen before that this error corrupts all subsequent calculations and makes the node tree kind of fail for each evaluation where this shows up. So this is not very good and something that we want to avoid. So for example, here I have this value -1, -2, and -3, and it goes and it is split and it goes through 3 power nodes. So basically here it's like I'm doing the power node for vectors. And so, of course, with 1, 1, 1, it's all good. I get -1, -2, and -3. But again, if I change these to 1.5, 1.5, and 1.5, I get not a number. So I want to avoid this. So one way to do to avoid this is do what we did with the scalars. I will make the absolute here. So let me, for example, copy this one here. I'm going to put it in here. And this will guarantee that my values are positive. And so I solve this as it was a positive value. And so now I don't get not a number. Now I might want to put this back into its respective sign. So basically I want to do a copy sign, but here I'm dealing with vectors, so I have to do it per channel. So this is a bit annoying, but yeah, well, again, here we go. So here is my value, and here is the sign that I want to be copied. So now I get these values. So they now are negative like they were before. Now what I'm going to show here is basically another way to go about copying a sign. So here I'm copying the sign explicitly with the copy sign node, and this costs me like 6 nodes to do. Now what if I want to do this multiple times? What if I want to copy this sign multiple times, for example? Well, I would have to have this 6 nodes for each of those, and that's not great. And so what I can do, for example, is to have some values that hold the sign and nothing more. So I can have something like the octants. Octants are a division of the 3D space into 8 portions. They are defined by the sign of the values. So for example, positive, positive, positive is the first octant. Negative, positive, positive is the second. Negative, positive, negative is the third octant, and so on. And so we can quickly define them by a position. So in this case, since they are all positive, the position is going to be 1, 1, 1. Here, the x-axis is negative, so it's going to be -1, 1, 1, and so on. So if I put my values in this format, this is something that I can multiply them by to copy the sign. So let's look into that. So I'm going to put let's do this to let's say to the sphere. Let's see what this looks like without the absolute. And so I have this thing going on. With 1.5, I'm going to have the point positions that have a negative value to fail, and that's why they disappear. I don't even see them like in the back face or anything. If I put the absolute value here, now I see them in the back face. So they're not corrupted. The calculations are not corrupted, and they show up. Of course, if I come here and I scale this down, you can see they're actually there. They're just all clumped together. Okay, so how do I restore their sign, their position, their octant position without using the copy sign? Well, I could also apply in a way a split vector with, say, a logic node. Logic, and well, instead of doing it, I'm just going to show the compound that I've already done, and where I basically split the vector and check if let's see, I'm going to copy this one. I'm going to copy the initial point positions. I want to check their sign, and so what I'm going to do is I'm going to check if the value of these positions is greater or equal to 0. If it is greater or equal to 0, I output 1. If it's not, I output 0. And I'm going to do that per channel. So I'm going to end up with something that is either 1 or -1 per channel. So something that relates to these coordinates of these octants. Okay, so now I have that. If I multiply that output, vector multiply, I come here and multiply this, I basically get this here. And so now they are back to their respective octant. In a way, what I'm showing here is what I've done here for this power compound. So I have the same thing, the object spot going through, and some values to be used as power. We'll put this, for example, 222. And so when I put this here, I get the same thing that I had without recovering the sign. But when I put the second port that has a ± sign on it, I basically recovered the sign. So now I have this sort of power node that acts per channel. So I can control the power amount per channel. If you don't need to do this per channel, you can also use the simple color corrector by the B&W tools, which the gamma input will perform a similar operation to the vectors. You only have to be careful to input the absolute value, because if you input negative values, it's not going to throw an error like the power node, but it will output the value as it was before, so it's not going to do anything to it. So again, I have to pass an absolute value. I then apply the power function here with the gamma input. Just know that the gamma input is the multiplicative inverse of the power input. So that's why I have this divide node where I divide whatever value I'm using here by 1, 1, 1. And so this will give me, instead of this, it will give me this. And then afterwards, I multiply by the sign that I've shown in here, so that I can put the values back into their respective quadrant. And so this is what I get as I change this here. So in this case, I have the same power value for all three channels. You notice that when I move the y-axis or the z-axis, it's not going to do anything. Only the x channel data matters here. And so I get this sort of effect in here. Right. So let's just look into yet another way to perform the sign. And it's just that sometimes you can be creative with vector data itself without having to always split and make vectors. So let's look into that. Going to turn on VPR, turn off Studio Live, and come here. And so what I have here is my sign compound that I had before. If you notice, we have an output that outputs the IDs. And so this is the ID of the octant, as I have here, the first octant, second, third. Of course, in this case, it's 0, 1, 2. It starts at 0. And I can do that to perform like decisions. So here, I just have it applied to a gradient, but I could have keys on specific integer numbers and have different things apply there. But so how could I do the same thing that I'm doing here, but without splitting the vector? Well, one way to go about it is to use an absolute node and divide that. Vector divide. So what this is going to do is let's say I have a value, and I'm going to divide it by the absolute of that value. So if x is, say, -5, I'm going to divide it by 5. This will give me -1. If x is, say, 3, I'm going to divide it by 3, and so this is going to give me 1. So if the value is negative, it's going to give me -1. If the value is positive, it's going to give me +1. So this allows me to get back into this format. So if I put this in here, you can see that, oh, sorry, not this one, you can see that I get the same thing as with sine. The only gotcha is that this solution here doesn't handle well when 0 is present. So here I have -205, and out it comes -101. So I was expecting a 1 in there. So if I put this in here, you can see that it comes a 1 on the y channel. So for this specific one, to account for these situations, I would have to, for example, put another absolute node here, invert, or just subtract the value to 111. And so instead of having 101, I get 010, and just add that to my initial value. So now I get on that format of ones, just like I have in here. So this is, of course, I'm using five nodes in here. Here I'm using 5 as well. So I mean, it's the same amount of nodes. This one might be a bit more explicit about what it's doing. This one might be a little bit more confusing. But let's say that you already have this for some reason. Well, maybe it doesn't cost much to add this to your current setup, and so you don't have to always use the splitting and make vector operations. But this is just one example of if you are creative with the vector operations, sometimes you can pull out the same things that you would normally run into a split make vector operation. So next I'm going to talk about position vector and 3D space fundamentals.